Here. I hope you can all hear me. I'll try to give a brief overview of liquid crystals, maybe from a physicist's point of view. And of course, I can't really cover the entire field, but I hope that I can give enough of an overview that it'll put some of the subsequent talks into something of a context. So let me begin. I'll say a few words about the history, maybe 10 minutes, because it's quite interesting. And then I'll talk about liquid crystal materials and phases, orientational order, which is really the key aspect of liquid crystals. I'll talk about free energy and the phase behavior. And then I'll say a few words about the effects of external fields. This is really an important aspect. Some thoughts about symmetry considerations and a brief summary. So the first point I want to make is that liquid crystals are really ubiquitous. They are everywhere in liquid crystal displays, projectors, Kevlar, the bulletproof fabrics that the police vests are made of, spider silk, silkworm silk, biological tissue, cell membranes are liquid crystalline, soaps, the slime of slugs. The transport of fats in our bodies is mediated by liquid crystal phase transitions. High-strength plastics, crude oil has liquid crystal asphaltene in it. Many insects have highly reflective liquid crystalline coatings. There's all kinds of new devices. So they're really ubiquitous. And it turns out that they've been around, they've been recognized for some time. The first observations of birefringent fluids took place in mid-1800s, and it turns out that myelin from nerve tissue forms a kind of a curious birefringent liquid material, and there are these so-called myelin figures which look to be alive almost. They grow and they ride and they change their shape. And many people studied these essentially using a microscope and polarized light. But the discovery is credited to Reinitzer, who was a botanist, and he isolated cholesterol nanoate from plants. And he found that when he heated the crystal, it first underwent a transition to a hazy liquid and then at a higher temperature to a clear liquid. So there appear to be two melting points of this material. This had not been seen before ever. And so this kind of observation was disruptive. It didn't fit into the conventional framework of how materials behaved. And so the early work was viewed with considerable skepticism. So Reinitzer then worked with Otto Lehmann, who was the first person to introduce a temperature-controlled stage to a microscope. And they carried out a systematic study, and Lehmann coined the word liquid crystal. So the situation was that there was some materials that showed a conventional crystalline solid phase and an isotropic liquid phase, and there was something in between, and the something in between was then claimed to be a new phase of matter, the liquid crystal phase. Charles Mogan studied these materials. By then it was sort of known that the molecules were elongated and isometric things, and that they could be aligned by aligning the surfaces. And Mogan showed that the polarization of light tended to follow the orientation of the molecules. And so long as the spatial period was much longer than the wavelength of light. Then Georges Friedel introduced a systematic classification of liquid crystals. He defined nematic, smectic, and cholesteric phases, described the nature of defects and the effect of fields. So this was in 22, and then in 1931, Fredericks showed that there was an interesting sort of phase transition. When you apply an electric field to a liquid crystal, there's a critical field above which the liquid crystal undergoes a structural transition. Unfortunately, he died rather young. But the point is that quite early on, the stage was set for optical applications. people understood there were birefringent fluids which controlled the propagation of light. They could be aligned, they could be reoriented by fields, and the first patent involving television was filed in 1936 already. But then the Second World War came along and much of the research came to a halt. So then in 1948, George Gray started to synthesize liquid crystals. This was a really not a very active area of chemical research. There wasn't much research money. He wrote a book. And in 1970, he developed these stable cyanobiphenyls, which became the workhorse materials of the early displays. And then he won many, many prizes. He's probably the most influential chemist in the field. So that the typical molecule is this so-called 5CB, which is 2 benzene rings, a cyanyl group, and an alkyl chain. Then there were some other important people. Jim Ferguson was studying cholesteric liquid crystals at Westinghouse. These are liquids, but they have a periodic, spatially periodic structure, and they show strong Bragg reflection of light, and they change their period and color with temperature. And Ferguson proposed to use these materials to monitor body skin temperature and to use it in tumor detection. Ferguson has some 500 patents. He's a kind of an interesting guy with a lot of really productive ideas. At the same time, David Sarnoff, who was CEO of RCA, really had this idea of flat panel television, so much so that in the wall of his office he had embedded a big conventional television set to kind of inspire people. Then there was George Heilmeyer, who basically invented these guest host materials where you put the dye into a liquid crystal, and if you realign the liquid crystal, the dye is realigned and changes the color. In '65, the Liquid Crystal Institute was founded at Kent State, and Alfred Salpa and Jim Ferguson were both there. In '66, the first liquid crystal display was produced, which is a scattering display. If you apply a DC electric field to a liquid crystal, you get these convective hydrodynamic rolls, and these scatter light strongly. And this was the first liquid crystal display. And it's not very practical because it uses a lot of power. And then the architecture that ended up being most effective, the so-called twisted nematic cell, was developed by Jim Ferguson, who worked with Al Salpe at Kent, and at the same time Halfrif moved from RCA to Hoffman-LaRoche, and with Martin Shad developed the twisted nematic cell. Interestingly, at the same time, Bob Meyer built such a cell at Harvard and showed it to Fred Kahn. Kahn showed it to Edwin Land. Land invented the Polaroid camera. And he showed it to Land, and Land said, no, this is not interesting, it won't go anywhere. So anyway, so this is when the TN cell was invented. And basically it works like this. I'm sure most of you are familiar with it. Basically there are two pieces of glass with a polarizer. Light shining from the top goes through the polarizer. The polarized light follows the polarization of the liquid crystal, goes through another polarizer, reflected from a mirror, and it comes back out. So looking from the top, this looks like a shiny, transparent mirror. On the other hand, if you apply an electric field, the molecules line up along the field. The polarization of light is not rotated, so the light that comes through here is absorbed down here, and the segment looks black. And this is basically the way that essentially all conventional liquid crystal displays work. All right, so much for history. So on to liquid crystal materials and phases. So liquid crystals, at least from a physicist's point of view, are anisotropic constituents, that is anything but spheres, and these things have long-range orientational order, and because of this all the physical properties essentially become anisotropic. So a typical molecule, again, is this old 5Cb molecule. But it turns out that it's not only molecules that make liquid crystals, although they are probably the primary materials. So there are molecules which are rod-like or disc-like, and recently these bent core, so-called banana molecules became really popular. But macromolecules also form liquid crystal phases, DNA, for example. And there are even solid liquid crystals, which are rubbers, single macromolecule. There are molecular aggregates. There are materials where assemblies of molecules form rods, and it's these rods that are oriented. Now they're interesting in that they can change their aspect ratio at will, depending on the environment they find themselves in. Nanoparticles make liquid crystal phases, both naturally occurring minerals and man-made nanorods and things. Microparticles form liquid crystal phases, so these are micron-sized particles made by Mike Solomon at Michigan. There are active nematics, which consist of biological entities which swim around, but they form ordered liquid crystal phases. So, and of course one can go in the other direction in the length scale. It turns out that the nuclei in neutron stars, which are really very high density materials, these nuclei form liquid crystal phases, and the mechanical properties of the mantle of neutron stars are predicated on the liquid crystallinity of the material. And finally, on a very, very small length scale, even correlated electrons, that is, electron spins, form liquid crystal states. So, and this is work by Gil Lonzerich at Cambridge on this. So there's an enormous range of length scales and range of materials, all of which show liquid crystallinity, and this is all associated with orientational order. Now, orientational order has one key consequence. So there's this well-known Goldstone's theorem that says that broken continuous symmetry must give rise to low-energy excitations, and therefore these materials are exceptionally responsive. So broken continuous symmetry means that the broken symmetry phase, that is a liquid crystalline phase, is continuous. If you take an isotropic fluid and you cool it down, the direction of average orientation can be in any direction, so that's a continuous broken symmetry. And because of these Goldstone modes, these materials are very soft, that is, they're very responsive to almost any kind of stimuli. So that's what makes these materials interesting. And so you can imagine all sorts of stimuli, all sorts of responses, and the whatever $200 billion LCD industry is based on just this one coupling of the electric field to refractive index. Okay, but in principle, many, many other possibilities are there and are currently being explored. Okay, so the most common liquid crystal phase is the nematic phase, where molecules or anisotropic objects simply point on the average in some direction, and you can get some really beautiful pictures in a polarizing microscope. And of course, these are the materials that are used predominantly in displays. And so why do they want to align like that? And it turns out that it's both due to the energy. They can minimize an energy by pointing in the same direction because of the anisotropic polarizability. And turns out that entropically they're also favorable because they can pack better. So even though they give up degrees of freedom of orientation, they can move around in position space better, and so entropy favors it as well. Smectic phases are layered phases, and again, both energy and entropy prefer this layering in certain regions of parameter space. So interestingly, if you take hard particles with no attractive interaction and you pack them into space, they will form a layered structure, which might be a bit surprising at first. All right. Now, the materials may be chiral, so they can be handed, left or right-handed. And then one can get other interesting phases. One can get phases where the direction of average orientation rotates in space. So these are helical cholesterics, or there are these exotic cholesteric blue phases that are made up of these cylinders where there's twist in all directions as you move away from the axis, and then these cylinders stack in various configurations to be nearly space-filling. Smectics also form interesting chiral structures. So the bottom line is that there are many, many phases in addition to these two simple ones with increasing complexity, and I think there are still new phases that are being discovered. And in between these phases, there are phase transitions. So if you start at, say, with a smectic A phase at low temperature, when you heat it up, there's a phase transition into the nematic phase, and then another phase transition at some well-defined temperature to the isotropic liquid. And the same thing is true with the chiral materials as well. So, and finally, there are two types of liquid crystals, and this is really mainly for a historical distinction. There are materials whose phase behavior depends primarily on temperature. These are called thermotropic. And others where the phase behavior depends on concentration of a solvent, and these are called lyotropic ones. So these are essentially soap-type materials. So this is not so accurate because these guys depend on the presence of solvents as well, and these depend on temperature, but for historical reasons this distinction is there. So orientational order is the key aspect of these materials, so let's say a few words about that. So one needs to quantify orientation and then somehow the orientational order of an assembly of materials like this. And we need this to construct a statistical description and then to relate physical properties to what's happening inside. So the question is how to describe orientation in some effective way. And of course, most of the particles, at least the lowest order, can be thought of as rigid objects. And they, in principle, orientation can be defined by the Euler angles. So the orientational distribution function has all the information that you need. But it may be that the distribution doesn't explicitly respect the symmetry of the particles. And there may simply be too much information. Maybe it's not necessary to have all that information to have an adequate description of the behavior of the materials. So a couple of examples may be useful to look at. In magnetic materials, there's a magnetic moment per unit cell, and the order parameter is the magnetization, the magnetic dipole moment per volume. And in ferroelectrics, it's the same. There's electric polarization, and the order parameter is the electric dipole moment per volume. And so these are useful quantities, and they kind of give a hint as to how to proceed in liquid crystals. And these are vectors related to the symmetry of the constituents of the material. Now, in a nematic, to lowest order, one can imagine a nematic molecule to be like an ellipsoid or a rod, which is symmetric end for end. And one has to describe its orientation somehow. So one can put two unit vectors here, which are really equivalent, and then one can ask, what are expressions, mathematical expressions, which treat these two unit vectors the same way? And well, we can just take the sum, but that's not very good because that's obviously zero. Or we can form the outer product. We could make a dyad of these guys. Now this is much better. It turns out that that L2 is just minus L1, so these two things are the same. And so this quantity, this second rank tensor, is in some sense the right order parameter because it remains invariant if you rotate this thing n for n, and yet it describes the orientation perfectly well. One could continue this, but it's simply not necessary. So a good order parameter for an object like this is a dyad made from a unit vector along the symmetry axis. And for the sake of convenience, usually this is normalized and the trace is subtracted out. So the orientation descriptor is this little second-rank tensor made up of the components of a unit vector along the symmetry axis. And the order parameter is just the average value of this. So each particle in a system has an associated sigma orientation descriptor, and the average value of that is the order parameter tensor. And this then sort of carries the first relevant level of information about the orientation of the system. Now this is symmetric traceless tensor. It can be diagonalized, and one can then write the eigenvalues in this way because it's traceless. So S is a scalar eigenvalue that basically tells us to what extent the individual symmetry axes are parallel with the average direction, and S can go from 1 when everybody is aligned, when this quantity is 1, S is 1. But when all the molecules are perpendicular to this unique direction, then S is -1/2. So S goes from -1/2 to 1. And P is a measure of how much symmetry is broken around the preferred direction and hat. So this is a measure of so-called biaxial order. In many cases, P is equal to 0, so in many situations one can ignore this term. Okay, so there's this order parameter tensor, which can be written as a scalar measure of order and something constructed from the eigenvector, which is the direction of average orientation. So this order parameter tensor written in terms of, in a uniaxial case where the system has cylindrical symmetry, in terms of the scalar order parameter and the director, this nematic director, that's the direction of average orientation, and the eigenvalue S gives some measure of how well things are aligned in that direction. And I want to stress this because these quantities will be appearing subsequently. Okay, but it's interesting to ask, suppose we had some other shapes. Suppose we had tetrahedra, for example. What would be the order parameter? And how would we deal with it? So somebody gave you a bunch of tetrahedra and said, are these orientationally ordered? How would we tell? It turns out that the order parameter in this case would be a third-rank tensor. But this is already interesting to some extent because we don't know how to decompose third-rank tensors into eigenvalues and eigenvectors and things. And it turns out that there is some theory moving in this direction by Lenny Fell back in '95, and then Tom Lubensky has also done some work on this. So the new kinds of liquid crystals that are emerging have symmetries other than the very simple one that I showed you before, and it's interesting to ask how one would deal with particles of higher symmetry. Okay, so in describing nematics, there are basically 3 levels of description. Some people only talk about the director, other people talk about the Q tensor, and other people still talk about the entire probability distribution function, and one finds these 3 levels in the literature. Now, free energy and phase behavior. So to understand the equilibrium configuration of systems, one needs to minimize the free energy. So the free energy is basically the interaction energy plus the contributions from entropy, and it's this quantity that has to be a minimum in equilibrium. So one somehow has to construct the free energy and then minimize it with respect to the order parameter, and then we know more or less what happens. So the free energy, a kind of a fairly robust definition of the Helmholtz free energy density, is this quantity here. So one basically needs to enumerate all the possible states, and this is the density of states with energy E, and then one has to sum this over all orientations omega and positions R. So one has to try to evaluate this quantity somehow for the system, take the logarithm, and that's it. And this turns out to be equivalent to the average energy minus Ts, where S here is the entropy. So to some extent, the business is to write down a free energy and to minimize it. And the first free energy that was introduced is by Frank and Oseen, and this is basically just the elastic energy associated with the spatial variations of the director, the direction of average orientation. And these are sort of canonical deformation. The splay corresponds to this. Twist, how can I show twist? Twist corresponds to this, and bend corresponds to this kind of. So these are the three canonical deformations, and these are just elastic constants, and to understand what a liquid crystal will do, one needs to minimize this quantity subject to some boundary conditions that I'll talk about in a minute. Now interestingly, if one starts to look at these director fields, one finds singularities, and these are defects. So you can imagine, and I will show you some structures where these kinds of things occur naturally. So except for at this point, everywhere along here, the director field is smoothly varying, but here there's a singularity. And now it turns out that this is kind of a problem because the free energy blows up at the singularity, and it's not so obvious how to deal with this. Probably this is a shortcoming of this particular director description. But nonetheless, these defects exist, and their behavior is kind of an interesting subject of study. Now, in the original paper, Frank and Oseen put in a couple of surface terms. So these are divergences, so that can be taken to the surface. And there are two of these. And it turns out that this one here is really a problem, because this term makes the free energy unbounded from below. That is to say, if you include this term, you can make the free energy as negative as you like. And that's obviously a major problem. So this wasn't noticed early on. Saupe, again, introduced this, but it was only in '89 that Oldano identified this problem, and it's called the K13 problem. And many papers have been written on this, and there have been sort of almost religious wars on this topic. But it still stands somewhat unresolved today. So I think it's kind of a fascinating problem. Moving on. There's also a beautiful analogy that Dejean pointed out between superconductors and smectics. So, as we all know, when you cool a superconductor into the superconducting state, the magnetic field is expelled. That's the Meissner effect. And if you have a smectic liquid crystal, which is a uniformly layered structure, it turns out that if there are no defects, this line integral around any closed path of n must vanish, because you're just counting the layers as you go around. And so then it follows that the curl of n must vanish inside the material. And in the elastic energy I showed you, there were two terms with the curl of n. And so in the smectic phase, that curl must vanish, so the elastic constants have to diverge as you go to the phase transition. So one sees the analogy of a superconducting transition, the divergence of these two elastic constants to expel the curl of n, which is like the Meissner effect. All right, mean field theories. So mean field is basically a simplification where the interaction energy with neighbors is replaced by the interaction of a particle with an effective so-called molecular field. And the first person who constructed a mean field theory was a famous physicist, Max Born. Unfortunately, he got the symmetry wrong. He assumed the vector order parameter, and the theory was unsuccessful. The first successful theory was constructed by Alfred Saupe in '58, who basically assumed London dispersion between the particles, which is just essentially the usual predominant van der Waals interaction. Polarizability, in our case sigma, contracted to make a scalar over 1 over r to the 6th. So this originates in 0-point quantum fluctuations, but the structure looks like this. And so this means that the average energy of a single particle is this term averaged over the neighbors, which just gives us the tensor order parameter. So this is the single particle potential in Mayer-Sapa theory, and this term has to be subtracted to correct for overcounting. So this is just a consequence of looking at pairwise interactions. And then once one has the energy, one can stick it in here and then immediately derive the Mayer-Sapa free energy in terms of the order parameter tensor, and then minimizing this gives the equilibrium value of Q. So one then gets a self-consistent equation, so this order parameter appears both here and here in the exponent, and then one can solve this numerically. So one gets, writing things in terms of the scalar order parameter, it looks like this, and one gets a self-consistent equation for S. Basically, this is just the second Legendre polynomial, and S appears here as well as here. So, and when you do all this, what does it look like? Well, it turns out that there are two solutions. So S equals 0 is always a solution. So the disordered phase is always a solution. Free energy is 0. The other more interesting solution looks like this. And this is the corresponding free energy. So this branch corresponds to this branch up here. And then if you were to heat up a sample, it would move along here, and then at this point it would fall down to the isotropic solution. On the other hand, if you were heating the material, it would do the other thing. And so one can superheat and supercool these materials, and the actual phase transition occurs at that point there. So this is the phase behavior, typical first order phase transition. It works like this. So now the Mayer-Sapa description is very nice, but it's a little complicated with all these integrals. So one can simply expand this term here as a function in a power series, a Taylor series in Q, and then one gets a Taylor series expansion, which is called a Landau expansion. And interestingly, the coefficient of the quadratic term changes sign, and that is responsible for the phase transition as a function of temperature. So this kind of expression is called the Landau theory, and then one can again minimize this with respect to the order parameters and get essentially the same behavior with maybe a few more order parameters that come from the expansion. Few more parameters that come from the expansion. Now, in addition to attractive interactions, there's also hard particle interaction. And Onsager developed the theory of packing of hard rods back in 49. And he found that if you pack enough of these into a fixed volume, they will also order. And the basic idea is that if you have two rods, one of them will exclude a certain volume to the center of the other, and this excluded volume depends on orientation. To lowest order, one could write it in this form. And then, evaluating the free energy, one finds that there are two terms. One term is sort of the typical F log F term, the pure entropy term, and there's another term involving the excluded volume. And then forging ahead, one can get a self-consistent equation for the distribution function if one minimizes this, and then one can get from the distribution function whatever one wants. So that's another hard particle aspect, which gives actually somewhat similar behavior as Mayer-Sapa theory. Now I want to say a few words about the effects of fields. Just checking the time here. We have quite a bit of time. Good. So if you put an anisotropic particle like this into an electric field, it turns out that the induced dipole moment is not along the electric field, because the polarizability in one direction is greater than in the other. So the dipole moment depends on the difference between these two polarizabilities. And if you take the polarizability, the ratio of P to E, then one gets this expression, which essentially ends up being just a linear term in the order parameter tensor. So the average polarizability of a system of particles, again, is linear in the order parameter tensor. And then if you look at the dielectric properties, the dielectric tensor just depends on the polarizability, and it turns out that the dielectric tensor, again, is linear in the order parameter. And one can write this in terms of, again, S and N for simplicity. So again, it looks like a term linear in the order parameter dyad, the director dyad. Now, interestingly, the anisotropy in these materials is pretty big. So the anisotropy, the difference in the two principal values, is just as big as one of them. So that's an important aspect in the electrical case. In the magnetic case, the anisotropy is really small. So although these materials respond to magnetic fields, the response is not so strong as in the electric case. And then one can put this additional field contribution into the free energy, both in the electric and the magnetic case, and either in terms of Q or in terms of the scalar order parameter and the director, and the terms look like that. And so now this additional term is important, because if delta epsilon is positive, as it is for most rod-like molecules, this means that to minimize the free energy, N wants to be parallel to the electric field. So the molecules like to align with the electric field, and this is then the mechanism that essentially all displays are predicated on. You align the molecules by applying an electric field. Okay. And if one looks at the free energy and asks how much work do I have to do to rotate the director a little bit, it turns out to be this quantity. So this is the torque per volume. It's just D cross E in these materials. And so if you put the molecule into an electric field, D will be not along the electric field, and this cross product will give you the torque that tends to rotate the molecule to be parallel to the electric field. Interestingly, optical fields also do the same thing. If you shine light at this molecule, the photons do something like go inside and travel in this direction and then come out. And due to effective radiation pressure at these points, you again get a torque in the same direction. So you can align liquid crystals not only by applied external low frequency fields, but also by optical fields. And so this is the mechanism used in conventional displays and projectors and things. And you can also use light to write images into liquid crystals. Okay. Now, what happens if the order parameter varies in space? So, well, in this case, one can construct three scalar terms from the derivatives of Q, which can be put into the free energy. And if you transform things back to S and N hat, then it looks like this, which is just the usual Frank terms. So there's a nice correspondence here. Unfortunately, it turns out that not all three of these elastic constants are independent now. Even though these are independent, it turns out that these elastic constants are not independent. So that's a bit of a problem, and people are still proposing various ways to deal with that. But these are the Goldstone modes. These are the low energy excitations which enable us to easily deform these materials. So it's interesting to look to see how big these coefficients are. So A, B, and C are the coefficients associated with changing the eigenvalue, the scalar order parameter, and the K's with just changing the director distortion. And just from dimensional grounds, you have free energy density, so A, B must have units of energy per volume. The only energy we have is the nematic interaction, so KT and I is a measure of that. And the only volume we have is a kind of a molecular volume. So B has to be this order. And Dergen showed essentially by a similar argument that K had to have units of KT over L because it has units of force. So Dergen told us that. Now if you wanted to change S, then the free energy cost would go as KT over L cubed times the change in S. But the cost of varying N goes as KT Q squared, where Q is the wave vector of the spatial deformation. And if you look at the ratio of these two things, it turns out that if the distortion wavelength is much larger than a molecular length, then this ratio is really, really small. So this tells us that generally in nematics, the scalar order parameter is constant, but the director varies in space. I mean, that's a typical behavior. Now, near singularities, of course, this is not the case, but this is generally the case. And so this energy balance is kind of interesting. All right, surface interaction. So these materials have to be bounded by something, and there have to be interactions at the surfaces. And again, just arguing from symmetry again, every surface has a normal, so there's at least one normal, and we can make a scalar from the order parameter and this normal. And in addition, one can treat the surface somehow. One can rub it, for example, or make grooves. And then one will have another direction in plane, which is distinguished. And so one can have another scalar term. And writing this again in terms of the director, one has the standard Rapini popular form for the surface energy. So these are the boundary conditions, as it were, for minimizing the free energy to find the equilibrium configurations. Now there's one, I think, really interesting aspect of these materials. So if you write the free energy as the Frank free energy and the surface energy, imagine that you have a sample of size r, then the bulk energy will go essentially as r, because this term will go as 1 over r squared, and this goes as r cubed. But this term will just go as r squared. So it turns out that in this case, in these materials, for large samples, the surface dominates. And that's just opposite to what happens in conventional materials, where typically the bulk dominates for large samples. So this is an unusual aspect, and to some extent, this is why liquid crystals are capable of the behavior that is utilized in devices. And of course, surface preparation can take all sorts of forms: spin coating polymers, rubbing it, deposit other things, corrugate the surface, put photosensitive materials and photo treat them. So there's lots of different ways of dealing with the surface. So next I want to say a few words about symmetry considerations. And symmetry arguments have played an important role in liquid crystals always. And in physics, we sort of believe that what is not explicitly forbidden will occur. So if it's not forbidden by symmetry, it will be observed. Now, it's clear, for example, that if you want to make a scalar to put into the free energy, then you cannot have a linear coupling to E of the order parameter tensor, because you cannot make a scalar that way. So usually we have this quadratic term. On the other hand, if you allow gradients, then you can make a scalar. So So repeated indices means summation, the usual Einstein convention. So if you have a derivative, if you have the divergence of Q, that's a vector which you can dot with the electric field. So this is now an allowed scalar. And essentially, in a free energy, the coefficient of a linear term in E must be electric polarization. And so this means that if we have a spatially varying Q, we must have electric polarization. And if you write Q in this way, again as the scalar value and the director, and you take the divergence, you get three terms, and two of these are called the flexoelectric terms, proposed by Bob Meyer. So simply, if you have any kind of spatial variation of n, then there will be electric polarization as a consequence. And even if you have a spatial variation in the scalar order parameter, you must have electric polarization. So if you take a liquid crystal and you heat it locally just a little bit to make the order parameter a little lower in value here than here, then there will have to be electric polarization arising as a consequence of that. So I think there's a lot of interesting complex possibilities. Now, again, I'm sure all of you are familiar with the notion of proper tensors and pseudo tensors. So in physics, most quantities are tensors of some rank, scalars, vectors, and so on. And proper tensors are those whose components change sign when you invert the coordinate system for even powers, and the pseudo ones are the ones that change sign for odd powers. And it's useful to keep track of this distinction between these things. So there are pseudo scalars that you can form by taking the cross product and the dot product of three proper vectors. And if you have a chiral molecule, a handed molecule, then you can identify three vectors uniquely. And you can make a pseudo-scalar from these three vectors. So handedness, chirality, is intimately associated with the presence of pseudo-scalars in a system. And interestingly, if you consider a system which is a tilted smectic system, there will be a director, which is a dyad, and there will be a layer normal, which again is a dyad because there's no way to tell which way the layers are facing, so to speak. And if the material is chiral, then there will be a pseudo-scalar. And it turns out that from these three quantities, you can form a proper vector. And if there's a proper vector in the system, there must be ferroelectricity. If you know that there's a vector in that system, the electrons will know that there's a vector there. And so it turns out that these systems must be ferroelectric. And Bob Meyer predicted on a similar argument that chiral tilted smectics must be ferroelectric. And since then, 50,000 materials have been synthesized based on this simple, elegant symmetry argument. And these materials are now used in all sorts of displays. So today, banana molecules are fairly popular. And these are not chiral molecules, but they form chiral phases. And the argument, again, is very similar. They have a director, they are smectic, so they have a layer normal. They have electric dipole moment, so there's electric polarization. And one can form a pseudo-scalar, and so the system can be chiral. So I think the symmetry arguments are powerful in both understanding behavior that is observed and also in predicting the behavior of new kinds of material. Okay, and this is a picture, an artist inspired by this symmetry argument. All right, so that's pretty much the end of my talk. So the first point is that orientational order is really ubiquitous, but I don't think that the consequences are fully understood, and there are many new systems on the horizon. Liquid crystals are inherently soft, mandated by this broken continuous symmetry, so they're really responsive. That's their singular characteristic. And I think symmetry considerations give insight into the behavior of these materials. I think there are significant challenges in modeling and in describing the defects, ill-conditioned minimization, and so on. So I think there are lots of interesting problems there. And I think there are really interesting prospects for the future in terms of new responses in existing materials, new materials with new symmetries, and new applications to come. Thank you.
Okay, thanks very much. We've got a minute for questions.